Okay, welcome back to quantum information theory. First of all, let's briefly recap what we did last time. So last time we finished our chapter on quantum measurements, and we then discussed composite quantum systems. So there we've seen that if we have a bipartite system with Hilbert space HA of the first system and HB of the second system, then the tensor product of these Hilbert spaces is the Hilbert space of our composite system. So we discussed the tensor product and also tensor products of states and how we perform, for example, the partial trace, right? In the end of last lecture, we've then seen that there are some very interesting states, namely those pure states which cannot be written as a product state, and we called this pure bipartite states which cannot be written as a product state, we called them entangled. And we also learned some particular entangled states, namely the so-called Bell states, which we said are maximally entangled state. And today we're gonna learn how we're gonna decide whether a state is entangled or not. So suppose that you are given a pure bipartite state, how could you actually decide whether this state is an entangled state or not? Okay, this is the next thing that we do, and this, the way how you're going to decide this is, for example, via the so-called Schmidt decomposition, and this is our next topic. This is 1.4.5. And the Schmidt decomposition is a theorem, so it's our theorem 1.8. Called Schmidt decomposition. And it says that suppose psi, which is in HA, tensor HB, is a bipartite pure state. Where the dimension of the component HA is dA, and the dimension of the component HB is dB. Okay? Then the Schmidt decomposition theorem says that then there exists an ON basis, say Vj of the Hilbert space A, and an ON basis Wj of the Hilbert space HB, such that we can write this bipartite state as a sum over some coefficients lambda or square root of lambda j times Vj Wj, where these coefficients, where this coefficient square root lambda j are strictly positive real numbers. Satisfying that the sum over the squares is equal to 1, and these coefficients are called the Schmidt coefficients. And I forgot one thing, namely the sum runs from j equals 1 to d. Okay. And d, what's d? D is smaller or equal than the minimum of the dimension dA or dB. Is the so-called Schmidt rank. Or sometimes also called Schmidt number. It's the number of non-vanishing Schmidt coefficients. Okay, so this is the Schmidt decomposition theory. And now you possibly wonder why we need this. So first of all, okay, the proof. You're going to do the proof as an exercise on the next exercise sheet. And the proof is not too complicated. So what you're going to need, therefore, is the singular value decomposition. So you remember possibly the singular value decomposition. And with this, you can prove the Schmidt theorem. Now, okay, now you wonder, why is this actually important? Or what is the benefit of this Schmidt decomposition? So this is the first remark. So usually, if you have a bipartite state, so suppose psi is a bipartite state, and suppose this x and this set of state vectors y are any or n basis of the Hilbert space HA and HY, AB, sorry, respectively. Then we usually write the state psi as a sum over these coefficients j and k with some complex values psi j k, and then we have the basis states x j tensor y k. Okay. So this is given any 2 or n basis. We usually express it in this way because we have to sum over all basis states. And here we see that the sum is running over 2 coefficients. Okay? J goes from 1 to the dimension of the first Hilbert space, and k runs from 1 to the dimension of the second Hilbert space. So the sum runs over dA times dB summons. Okay, this can be a very, very large number. And now you see the benefit of the Schmidt decomposition here. Here the sum has only one index, so it only runs from 1 to d, where d is the minimum of these 2 dimensions. And this is the actual benefit of the Schmidt form, that we are not having such a clumsy sum, so we can reduce it in this form. Okay? I hope you can see it. And the theorem says that for any bipartite pure states, you can find such bases, v and w, such that you can write it in this form. Okay? And now what's the actual... Okay, the next point why this is interesting is the following. So suppose now that we have such a state psi in HA tensor HB, and we like to calculate now the reduced state of subsystem A or the reduced state of subsystem B. Okay, and what we'll see in a second is it turns out that these Schmidt coefficients here, so the squared Schmidt coefficients, which are these lambdas, they are the eigenvalues of our reduced states. Okay, so if psi is in HA times HB, then the Schmidt coefficients, so this actually the squared Schmidt coefficients, lambda j, they are the eigenvalues of the reduced density operator rho A, as well as of the reduced density operator rho B. Okay, and this we can prove. Okay, let's prove this. So let's calculate rho A, which we know is the trace over subsystem B of this state. And now we plug in the state in Schmidt form. So we have the trace over B of a sum over jk, and then square root of lambda j, lambda k, and then we have vj wj, and here vk wk. So it's sum over jk, square root lambda j, lambda k, and then as a trace we have the trace of wj wk times vj vk. So if you remember, this is how we perform the partial trace. Means we are tracing only over the second component of our composite system. So this trace gives me something like wk wj, and since these w's forms an ON basis, it's nothing else but delta jk. Okay, so means that our sum reduces to one index. So it's the sum over j and then lambda j times vj vj. This equation 1.52. And okay, what's this form here? Here we have an ON basis, and the sum is only running over one index, and then we have these real and positive coefficients lambda j. So this is nothing else but the spectral decomposition of our reduced state rho A. Okay. And since this must be the spectral decomposition, we find that those lambda j's are the eigenvalues of rho A. Okay, which is a proof of our statement here. And now the same thing can be done if I instead trace over subsystem A. Okay. So similarly, we find, I think you can either you already see this, or it takes a two-line calculation, that rho B is the sum over j, lambda j, and now the basis vectors wj. Okay, so rho A and rho B have the same set of eigenvalues, and these eigenvalues are the squared Schmidt coefficients. And this is now interesting to see. Okay, we will come back to this observation in a second. The next thing is a statement that we can prove very easily, is namely that a state okay, so state psi in HA tensor HB is separable, or is a product state, is a product state if and only if it has Schmidt rank d equals 1. Okay, so the proof is fairly simple. First, let's go in one direction. So we say that we have a product state. Okay? If you have a product state, then we can write in such a form such that there's no sum, right? Because this is a product state, meaning we have Schmidt rank 1. There's only one Schmidt coefficient, and this Schmidt coefficient must be 1. Okay? Now the other direction, if we have Schmidt rank 1, then also the sum vanishes. Then we have a product state. Okay? So we prove the statement. And from this it directly follows that psi is entangled if and only if it has Schmidt rank d greater than 1. So this says that if we have a Schmidt rank d greater than 1, then we cannot write this as a product state, meaning that it must be entangled. And our last remark here is that the Schmidt decomposition cannot be generalized to more than 2 parties. Okay? So this form, you can, in general, for every state, you can find this form only for a bipartite state, but not for partitions with more than 2 parties. The Schmidt decomposition cannot be generalized to more than 2 parties. With this, we now found a way how we can show whether a state is entangled or not. So the only thing you have to do is you have to find the Schmidt form. So you have to find these eigenbases and write it down in this way. And then you can find out whether the state is entangled or not. So the next thing you see, I'd like to stress this here, is that if you have an entangled state, then your reduced states are mixed. Okay? Take a look at this equation here. So these are your Schmidt coefficients. If you have an entangled state, then you must have more than one Schmidt coefficient, meaning that your reduced state is mixed. Right? If you have a product state, so a state which is not entangled, then your reduced state is also a pure state. Okay? So automatically, if your state is entangled, you get a mixed state. And indeed, as we will see at the very end of the lecture when we discuss entanglement theory, the mixedness, so a measure of the mixedness, for example, the purity, gives us a measure of how entangled such a state is. Okay? But in order to quantify entanglement, we need much more ingredients, and that's why we're going to discuss this at the end. But so here you can already see that the more mixed it is, the more entangled the state is. Okay? And So what we've done here in this calculation is we started from a pure bipartite state. We traced out one system, and we got the reduced state as a mixed state if there is entanglement. Okay. Now we're going to ask the question from just vice versa. Suppose that we are given a mixed state. Can we now enlarge our Hilbert space and consider an additional reference system such that we define the state on this composite system with this additional reference system, and such that the state is then pure? Okay, this is called a purification. That's what we're going to discuss next. It's chapter 1.4.6. So suppose we are given a possibly mixed state, or a mixed state rho A, or let's call this now rho S. I call it rho A, which is a density operator on the Hilbert space HA. And we introduce a fictitious reference system. Okay, it's important, it's a fictitious system. So this is what we want to do. In addition to our Hilbert space, we now introduce a reference system. So this is a reference system. We simply say, okay, what if there is such a system? Take this, define a state on this system such that if we trace out our reference system, we get back our mixed state rho A. Okay? And such a state, psi, is called a purification. So this gives rise now to this definition, 118. A purification of a density operator rho A is a bipartite pure state on the composite system HA and a reference system HR with the, how do you say, the property that write it down here, that rho A is equal to trace over the reference system. So you might wonder why we want to do that. Okay? The reason is that in quantum information theory, if you perform proofs or longer calculations with mixed states, it's often complicated. So it might be easier to deal with pure states. And in this case, what you can do is you can introduce such a reference system, calculate with pure states, and in the end of your calculation, trace out this reference system. And that's actually the reason why we introduced this here. And at some point, we are going to come back to this method. Okay? If we discuss quantum information theory, which is discussed in more detail, the second part of this lecture, then at some point we're going to use this technique. And now the question comes up whether we can always find such a purification and how this purification would look like. So, meaning given such a state rho A, what would I have to do such that I get a purification? Okay? So this is our first remark. It says if rho A has spectral decomposition, rho A equal to, let's call this eigenvalues now dj, and the eigenvectors, let's also call them dj. So this is our spectral decomposition with eigenvalues dj and the corresponding eigenvectors. And further, let the set Rj be any ON basis of the reference system HR, then psi is equal to sum over j square root of dj times dj Rj, then this is a purification of rho A. And we can easily see this if we take the state, plug this in this equation here, 1.54, meaning tracing out the reference system, and then we should get back rho A. Okay, we're going to do this now. The calculation is exactly this calculation here, so I leave it here for the moment. Only erase this part, because we're going to do the exact calculation now. So let's plug in this state 155 and 154. So proof plug 1.55 into 1.54. So we get we get the trace R of psi is equal to the trace of sum over jk square root of dj dk, and then we have some dj rj dk rk. Okay, now note that this is exactly what's written here. So we are now tracing out the reference system, meaning the second subsystem. So it's equal to sum over jk square root dj dk, and then we have trace of rj rk times dj dk. This again gives us RK, Rj, and since we assumed that these state vectors R are an ON basis of our reference system, this gives again delta Jk, so we have sum over J, dj, and then dj, dj, which is our density operator rho A in the, okay, this is, sorry, in the spectral decomposition. Okay, so with this I want you to note the similarity here between the purification and the Schmidt decomposition. And with this, I'd now like to come to another topic, namely, we now discuss what's special about entanglement. And for this, we're going to discuss now the Bell inequality. Okay. So in the early days, I hope you can try to imagine how it was when quantum mechanics was founded. It was beginning of 20th century, and it was a very new theory, and it took some time for the people to accept that the theory gives the right predictions, right? So if you take the theory and you calculate that you get the right predictions for your experiment. However, this abstract, let me say this rather abstract formalism also led to a lot of debates on this interpretation, and there were some people who were always trying to find any controversies and trying to, in this way, trying to see whether quantum mechanics is complete or whether this really is a fundamental theory which describes what you want to describe. And it was particular, so many discussions were between Bohr and Einstein in the beginning, so it was around in the 20s or in the 1930s, where they discussed a lot about the interpretation also of the theory. So Einstein, for example, he always agreed upon the prediction of the theory. However, he was not satisfied somehow with this formalism. And his concerns were mainly on this interpretation of the theory. And in particular, in 1935, he published a paper together with Podolsky and Rosen, so it's the famous EPR paper. And there, they found in the formalism something which didn't fit to their interpretation of what a physical theory must satisfy. Okay? In particular, what Einstein, Podolsky, and Rosen, what they assumed is that a physical theory must be a local and real theory. And in particular, what they've seen is that if I go to composite system, say to a bipartite system, then there are states, which we now call entangled states. Okay, back then they didn't know about them so in detail like this, or they didn't call them entangled so far. And so back then they found that there are such states which kind of violate their intuition of what a physical theory must satisfy. So in particular, they said, okay, a theory must be local and real, so it must satisfy some conditions. And they found that with these particular entangled states, kind of this violates their intuition of the interpretation. And they said, okay, there could be a way out if we, for example, introduce what are so-called local hidden variables. Okay, they said, okay, if we complement the theory with something more that we didn't put in our formalism yet, then we could get rid of this problem. Okay, and in the 1930s, this was simply a matter of taste or a question of interpretation. And no one actually thought that there could be a relevance in an experiment where this could be checked. And it took until the 60s, and I think it was in 64. It was in 64 where John Bell presented the so-called Bell inequality, which now gave experimental testable equation in order to check whether we do have to complement our quantum theory with these local hidden variables, right? And this formalism of Bell, so Bell's inequality, it's more or less a very abstract thing, okay? And it took another few years until 1969, where there was Clauser, Horn, Shimony, and Holt, who took Bell's inequality and kind of rewrote them in a setting which can be experimentally accessed. Okay? And with this, they then kind of formulated a Bell inequality, which can be investigated in experiment. So meaning that you can perform experiments with which you can check whether we do have to add the local hidden variables in our quantum theory in order to explain entanglement. Right? And what we now discuss is this so-called CHSH Bell inequality, which is the inequality from Clauser, Horn, Shimony, and Holt. Okay. But before this, I'd like to briefly write down what Einstein, Podolsky, and Rosen, what they had in mind when they were speaking about reality, locality, and completeness of a theory. So this is chapter 1.5. So I'm not writing down the history itself. I think it's enough that I just told you some historical background, but let me write down what Einstein, Podolsky, and Rosen meant by reality, locality, and completeness. So in the sense of Einstein, Podolsky, and Rosen. So the reference is Einstein, Podolsky, Rosen. It's a physical review. '47. So volume 47, number 777, and it's in 1935. It's reality. So reality means, in their sense, that if we can, without disturbing a physical system, we can predict the value of the physical quantity, with certainty, then there exists an element of reality associated with this physical quantity. Okay, in order to understand this a bit more, you can simply imagine a two-level system, so say a spin, right? And say you have a spin, and if you now can predict the spin, so the value of the spin with certainty, then they say, okay, if this is real, so if our theory describes the reality, so to say, then there must exist an element of physical reality associated with this spin. Okay? So the spin is then not only something in our abstract formalism, but you connect it to something that is living in reality. And what's living in reality is what they call an element of physical reality. Okay? Meaning, now we can repeat this, because possibly it makes more sense if you repeat this 2 or 3 times. So if we can, without disturbing the system, predict the value of this spin with certainty, then it must be connected to an element of reality. So he draws the connection between our abstract formalism to the reality. Right? And this is, so to say, the reality condition. And the next is the locality. Saying that asserting the physical process occurring at one place should have no immediate effect on the element of reality at another location. Well, this is actually very intuitive to understand. If you have a bipartite system and you place them into different space-like separated places, and if you perform a measurement or you somehow disturb one of these systems, then this can have no immediate effect on the physical, on the element of physical reality of the other system. Okay, and it's important here that on the element of physical reality, so the element of physical reality at another place. Okay, so if the other one has an element of physical reality, then this cannot be immediately be disturbed by performing or changing something at another system. And then lastly, I'd like to write down what is meant by completeness. Namely, a complete physical theory must have a theoretical object for each element of physical reality. Okay, now with this we can understand why Einstein, Podolsky, and Rosen suggested that we would have to include these hidden variables, because they found that with considering such entangled state, they found that okay, something is wrong. This does not satisfy reality and locality, such entangled state. So a way out would be to introduce additional theoretical objects which can explain this entanglement. Okay, because they then thought possibly we missed something. We missed something and cannot explain all elements of physical reality. Okay, and with this, I'd like to finish this part of the history. And after the break, we are then going to calculate the CHSH Bell inequality from both perspectives. First, we take any real and local theory, and we try to, we assume that, okay, we have some entangled particles, but we assume a theory which is a locally real theory, and add some hidden variables, and then we will derive a parameter. And we're going to do the very same thing then by assuming the quantum mechanics is complete. So by using the quantum formalism that we introduced in the last 2 weeks, we're going to calculate the very same object, and then we will find that this, from a quantum mechanical point of view, this object can be different than from a point of view where we have a local real theory. Okay, this we're going to do after the break, so let us meet in 10 minutes. Okay, let's continue with our discussion of Bell inequality. So before the break, we learned a bit what is meant by reality, locality, and by completeness. And we are now going to calculate 2 viewpoints. The first viewpoint is going to be a viewpoint where we consider a locally real theory and with local hidden variables. And then we derive what is sometimes called the Bell parameter. And then we're going to do the same thing by considering that quantum mechanics is complete. Okay, so this is chapter 1.5.2. Okay, what we consider is the following setting. So suppose that we have 2 objects possibly coming from some source, and there are some hidden variables. Okay, we assign some hidden variables to them. So since they possibly come from the same source, they have the same set of hidden variables, which we call lambda. Okay, then we separate them, locally separate them, such that here's one object, carries the hidden variables lambda, and here's one object. And we then perform a measurement. Okay, this is the left side is our measurement apparatus A. And suppose that the outcome of the measurement, this is what we call capital A. So this capital A can be either plus or minus 1. And capital A, so the outcome can now depend on this local hidden variables. And it depends on small alpha, which is the setting of our apparatus. So alpha is the setting. Okay, and I get plus or minus 1. And the same thing here on this side. We have the measurement apparatus B. And as an outcome, I get capital B, which depends on our setting. of the measurement apparatus and the hidden variables. So this is now a local setting because the measurement here on the left side does not depend on this outcome, and it does not depend on beta. So it does not depend on the setting of the other apparatus. And the same thing here. Okay, so this is now a viewpoint from a locally realistic theory, and we added now these hidden variables in order to see, okay, what's now the outcome if there are such hidden variables. Okay. And what we assume is first, okay, these hidden variables, what is it? Okay, the hidden variables lambda, so can be a whole set of variables which are distributed according to the probability distribution rho of lambda, which are our probabilities, so it's greater or equal to 0, such that if we integrate over this rho of lambda, it must be 1. Okay, so rho of lambda can be either a single or a whole set of hidden variables. Okay, rho of lambda gives us the probability of this set of hidden variables lambda, such that we integrate over this gives 1. Okay, very simple. It's just a distribution. How are my hidden variables distributed? So this is a very general point of view of such hidden variables. This is equation 1.59. What we now calculate is the probability that we get a certain outcome. Okay? So the probability that detector A has outcome A of alpha lambda is equal to x, with x equal plus minus 1, is then, so the probability that we have the outcome A is x, is given then as an integral of the probabilities that I get the outcome A is equal x for some hidden variables lambda, and then we simply integrate over the lambda with the distribution. Okay? And this is integral d lambda rho of lambda times 1 plus x times A of alpha lambda over 2. So this is an x here. So this is the probability that detector A shows x. Okay? If x is equal to 1, then we have, if A shows x, this one gets 1. Okay? And then this integral over lambda. And if x is equal to minus 1, then you see that this gives 1 if A is minus 1 and 0 if A is plus 1. Okay, so this makes sense. If you don't see it so far, think about it one more time. But this is, you can see that this makes sense. And then similarly, the probability that the pair of detectors AB give the outcome x, y, where x and y can now be plus minus 1. So it's element this probability is then P, I call this Pxy, equal to the integral d lambda rho of lambda. And then we have 1 plus x times a of alpha lambda divided by 2 and 1 plus y of b from beta lambda divided by 2. Okay, now we define a correlation measure. E, we call this correlation measure E of alpha beta. So remember, alpha and beta are our settings of this measurement apparatus. And we define this as being the probability that both detectors show plus the probability that both detectors show minus, plus the probability minus the probability that we have plus minus, and minus the probability that we have minus plus. And this satisfies minus 1 smaller equal E of alpha beta small equals 1. Okay, so what this is nothing else than it measures how probable it is that we get the same outcome. Okay, if it is plus 1, we will always get the same outcome. So the detectors will always agree. If this is minus 1, you see minus is here and here, then the detectors will always disagree. Meaning that this is a correlation measure showing us, okay, how probable is it that the detectors agree or disagree. If they agree, then it's rather positive. If they rather disagree, it's negative. Okay? And we now can calculate this by plugging in this probability in this equation. So this is equation 1.62. So plug 1 point, what we're using 1.61 in 1.62 gives E of alpha beta is equal to this integral over d lambda rho of lambda, and then we have 1/4 and we have something like, I do have now shorthand notation, so we have a 1 plus 1 plus a times 1 plus b, and then we have plus 1 minus a times 1 minus b, minus 1 plus a, 1 minus b, minus 1 minus a times 1 plus b. Okay, we simply now use this. So let's see, the first term is p plus plus, meaning that x and y are plus. Okay, then we have 1 plus a half and 1 plus b half. Okay, this is what we see here. 1 plus a and 1 plus b, and this both times dividing by 2 is 1/4. And then the same here. So we have then here plus p minus minus, which is plus, and then since I have minus minus, I have 1 minus a and 1 minus b. Okay, but here we use the shorthand that a is a of alpha lambda and b is b of beta lambda. So otherwise it's getting too long, this expression. So let's simplify this. If you multiply this out, so this gives 1 plus b plus a plus ab This gives 1 minus b minus a plus ab. This gives minus 1 plus b minus a plus ab. And the last term gives minus 1 minus b plus a and plus ab. Okay, then things cancel. So we have here 1, 1, minus 1, minus 1. I use another color. So those cancel, 1, 1, minus 1, minus 1. Then we have plus b plus a, minus b minus a. And here we have plus b minus a and minus b plus a. Also cancels. And what remains is 1, 2, 3, 4 times ab. So we got an expression now for our measure. So far nothing really exciting happened. Now there comes an ingredient, which is sometimes called the Bell parameter, which is not easy to see why it is defined in the way it is defined. So people call Bell a genius sometimes because he did find this measure. So let us now next consider the angles alpha, alpha prime, beta, and beta prime. So we consider two different settings for each detector and define. So we define now this measures. We call it S of alpha, alpha prime, beta, beta prime, which is A of alpha lambda times B of beta lambda minus B of beta prime lambda plus A of alpha prime lambda times B of beta lambda plus B of beta prime lambda. Okay, so this is sometimes called Bell parameter, and it's a definition. Okay, so it tells us at this point nothing. The only thing is what we see is that it satisfies that minus 2 smaller equal to S of alpha, alpha prime, beta, beta prime, smaller equal to 2. Okay, how do we see this? So we see it if B of beta and B of beta prime, if they agree, so if they yield the same outcome. Okay, remember, outcomes are either +1 or -1. So if they yield the same outcome, this is 0. So the first factor vanishes, and this, if B of beta and B of beta prime is the same outcome, this gives either +1 or -1, and then times +1 or -1, which is either +2 or -2. Okay, so this gives +2 or -2, the parenthesis, And then here we have +1 or -1, gives either +2 or -2. Actually, must be like this. So I write it down like this, okay? So S is either +2 or -2. And what we do next is we are now calculating the expectation value of this thing here, okay? So we calculate the expectation value. What is it? It's the integral over d lambda, rho of lambda, and then S of alpha, alpha prime, beta, beta prime. And suppose that we are not only calculating the expectation value, but the square, the modulus of this expectation value. So let's take a modulus here. Then we find that this is smaller or equal to integral d lambda rho of lambda times the modulus of S of alpha, alpha prime, beta, beta prime. Okay, this we know. So actually this is element of ±2. So this we know must be 2. So we get S is smaller or equal to integral d lambda rho of lambda times 2, which is, so I can put the 2 here in front of the integral, and this integral we know. Okay, if we integrate over the distribution, the probability distribution, it's 1, so it's 2. Okay, so as a result, we get that the expectation value of this S, which is the expectation value, I now write it down in terms of these correlators. So if I use this expression here, I have A alpha, B beta, which is E of, if I integrate over this, I have E of alpha beta, and then I have minus E of alpha beta prime plus E of alpha prime beta plus E of alpha prime beta prime. Okay, do you see this line? Do you see this? Okay, it's hard to see. Okay, I do it into the calculation. If we plug this in here, I'll say here. Okay, so if we plug S alpha, alpha prime, B beta prime from 164 in here, and then we have always pairs AB, 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 AB with the sign of plus, minus, plus, plus, right? And we've seen that the integral d lambda rho lambda of such a pair here is our expectation value E, is our correlator E alpha beta. So we can express this in this form. And we know from this calculation from above that this must be smaller or equal to 2. Okay, so question 166. Okay, I do this calculation now here just to be complete. So we have S is equal, if you use this line here, integral d lambda rho of lambda S of alpha, alpha prime, beta, beta prime, which is integral d lambda rho of lambda. Now I plug in this expression here, which gives me A of alpha lambda B of beta lambda minus A of alpha lambda B of beta prime lambda plus A of alpha prime lambda B of beta lambda plus A of alpha prime lambda B of beta prime lambda. Okay, and now the modulus. Use the modulus. And if I now use this expression 163, then this gives me B of alpha beta minus alpha prime plus B of alpha prime beta plus E of alpha prime beta prime. Okay, and this is what's written here. So what we found by equation 166 is that we have that the modulus of this expectation value of S is smaller or equal to for any local realistic theory. So this holds for any local realistic theory. And what we're now going to do is we calculate this expectation value S, assuming the quantum mechanics is complete. So it's 1.5.2.2. It's a quantum mechanical description. So what we do is we suppose that quantum mechanics is complete and no hidden variables are required. So the setting is before. We have here a detector, here detector. We have our entangled particles. This detector B gives the outcome plus minus 1. And here in detector A also gives outcome plus minus 1. Okay. And such a setting where we have a bipartite system, two particles with outcome plus or minus 1, is, for example, given if we have a Bell state. Okay, we have a two-level system, and for two-level system, we can now assume, let's assume they are entangled and in a Bell state. So assume that the state is, so assume now Bell state, say psi minus, which is 0, 1, minus 1, 0. I think, consider this state over, yeah. So in this case, we are in the setting that we considered before, namely that we can perform measurements which give either outcome plus or minus 1. And to describe this measurement, we now need the corresponding observable. So we consider the observable m alpha is equal to alpha minus alpha plus p half and alpha plus p half. So where alpha is equal to, how did I define it? It's cosinus alpha 1 minus sinus alpha 0. And this observable is a Hermitian operator, and it has the outcomes m equals 1 and m equals minus 1. So if the outcome, so the corresponding measurement operator to the outcome 1 is this projector here. This corresponds to the outcome 1. Remember, our measurement is described by this observable, which is a Hermitian operator. The eigenvalues, which are plus 1 and minus 1, correspond to the outcomes. So outcomes are m1 and minus 1. The projectors onto these corresponding subspaces are the measurement operators corresponding to these outcomes. So the measurement operators are here, this projector alpha, and here this projector alpha plus p half. Okay? And you can easily prove that these projectors satisfy the completeness equation. So we have the completeness equation is satisfied since this quantity is the identity. Okay, it's an easy calculation, 2 lines or 3 lines if you don't trust me. Okay, what we're now going to do is we use the formalism to calculate this thing here, and therefore we first have to calculate these correlators. Okay, so these correlators are E of alpha beta, are now given by the probability that we measure the angle alpha, we have p alpha alpha, okay, because the alpha corresponds to the outcome plus 1, okay. This is so the probability plus plus, so to say, so it's p alpha alpha plus p of alpha plus p half and alpha plus p half, which would be p minus minus, right? Because the projector alpha plus p half corresponds to the outcome minus 1. And then minus p of alpha and alpha plus p half minus p of alpha plus p half and alpha. Okay. This is now simply the expression of these correlators. Now, in order to get an expression for this, we calculate the probabilities. So we have p alpha beta is equal to the trace of the projector on the state alpha on our first particle tensor, the projector with the angle beta on the second particle, okay, and then we have our state phi. So this is what we know from our measurement postulate. So calculating the trace gives psi, and then we have here alpha beta psi, which is the modulus of alpha beta psi squared. And now I use this expression here and the definition and our Bell state, psi minus. Sorry, this must be psi minus. So this is equal to modulus of, this one is cosinus alpha 1 minus sinus alpha 0, and tensor beta, which is cosinus beta 1 minus sinus beta 0. And then we have 1 over square root of 2, 0, 1 minus 1, 0. Now we multiply the first tensor product. So we have something like cosinus alpha, cosinus beta times 1, 1. And then we have minus cosinus alpha, sinus beta 1, 0. And minus sinus alpha, cosinus beta times 0, 1, and then plus sinus alpha, sinus beta 0, 0, and then we have 1 over square root of 2 goes out here, and here we have 0, 1 minus 1, 0. Okay, put this in parentheses. Modulus square. Okay, and then we see here, okay, 1, 1 has no overlap with this, so this cancels. Then same holds for 0, 0 has no overlap here. The only terms which remain is this and this one. And this one gives plus cosinus alpha, sinus beta. And this one gives minus sinus alpha cosinus beta, and this is nothing else. What's standing here is the sinus of alpha minus beta squared. Okay, and as a next step, we have now a single probability for two different angles, and we can use this expression in this in the upper equation. I didn't give it a number. It should be 1.69. So this using this in equation 1.69 yields that E of alpha beta is equal to, okay, we have then 1/2 and then sinus squared of alpha minus beta, alpha, sorry. Yeah. Alpha beta plus. Non-conformal. confused. Why? Sorry, because I did a mistake here. Okay, here I did a mistake. This must be beta. And this must be beta. And this also. And this also. Okay. Because at the second detector we measure at angle beta, right? Not angle alpha. Okay, now I'm not confused anymore. Now we can use this equation, plug it in here. So the first term gives 1/2 sinus squared alpha minus beta. The second term gives 1/2 sinus squared of alpha minus alpha plus p/2 minus beta minus p/2. And then we have minus sinus squared of alpha plus p/2 minus beta minus sinus squared of alpha minus beta minus p/2. Okay, so this one here is the cosinus squared of alpha minus beta. So the sinus squared alpha minus beta minus p/2 is the cosinus squared alpha minus beta. So we have then E of alpha beta is equal to, so this one here cancels, sinus squared of alpha minus beta minus cosinus squared of alpha minus beta. And this is minus the cosinus of 2 times alpha minus beta. This is equation 1.71. Okay, now we are almost there. So we have now expression for this, and we can now plug in this equation in order to calculate the expectation value of this S parameter. With this, we get that this parameter, which is E of alpha beta minus E of alpha beta prime plus E of alpha prime beta plus E of alpha prime beta prime. So we have cosinus of 2 times alpha minus beta minus cosinus of 2 times alpha minus beta prime plus cosinus of 2 times alpha prime minus beta plus cosinus of 2 times alpha prime minus beta prime. Okay. But what are alpha prime, beta, and beta prime? Well, we can choose them as we like, right? Because we didn't specify them. So let's choose them such that this gets maximal, okay? We choose, and I mean, it is not easy to see for which angles this gets maximum. I just state them here, and we're then gonna finish the calculation. So we choose now alpha is equal to 0 plus some arbitrary phi. Beta is equal to pi over 8 plus phi. Alpha prime is equal to 2 pi. No, I think it's 2 pi over 8 plus phi, and beta prime is 3 pi over 8 plus phi. Let me check this. Yes. Okay. So with this choice of angles, we can now finish this calculation and see what the expectation value will be. So we have cosinus of 2 times alpha minus beta, which is minus pi over 8, gives minus pi over 4. And then we have minus the cosinus of, what is it, alpha minus beta prime, which is minus 3 pi over 8. So minus 3 pi over 4 if you multiply it by 2. And then plus cosinus of alpha prime minus beta is pi over 8. So multiplied by 2 is pi over 4. Plus cosinus of, what's the last one, alpha prime minus beta prime. It's minus pi over 8 times 2 minus pi over 4. Okay, so let's check these values, see what the cosinus is. So here we have pi over 2, here we have pi over 4, where the cosinus is 1 over square root of 2. Same here at minus pi over 4. And then we have minus 3 pi over 4 is somewhere here, where it is minus 1 over square root of 2. So plugging this in gives 1 over square root of 2 minus 1 over square root of 2 plus 1 over square root of 2 plus 1 over square root of 2, which is 4 times 1 over square root of 2 or 2 times square root of 2. Okay, so what we found is now that there are instances where this Bell parameter is larger than 2. But before, we showed that for any local realistic theory, it must be bounded, so this parameter must be bounded by 2. Now, assuming that quantum mechanics is incomplete, we found a value larger than 2. And this now allows us that if we perform this experiment, this allows us to check whether this holds or not. And by this, it allows us to check whether we have to add local hidden variables to quantum mechanics or not. Okay? And these experiments have been performed. So for many decades now, actually. So the first experiments were in the beginning of the 70s or even already the late 60s. So in the 70s, say in the 70s. And from there on, there are many experiments which test these Bell inequalities. And if you trust these experiments, they speak in favor of quantum mechanics. In the sense that if you trust these experiments, then we learn that no local hidden variables are needed to complete our formalism of quantum mechanics. Yeah, and finally, I'd like to mention that this upper bound here, this is indeed the maximum that we can reach with quantum mechanics, and it's called the Zierelson bound. Okay, probably hear this sometimes. It's not so important, but it's important is that this is really the upper bound. So in general, what do you find? That for a quantum mechanical description, you find that this parameter is smaller or equal to 2 times square root of 2, okay? Which is larger than 2. And with this, I'd like to finish this lecture for today. And I see you next time on Monday.